Data Analysis Part 10, Methods for Quantitative Imaging. Hello everyone, welcome to this Part 10 of the Data Analysis course. In this video I want to look at methods for obtaining quantitative numerical results from image data. First of all, very briefly in general, and then with some particular examples of dealing with some sample data using some basic image processing methods in Matlab. Sample code and sample image data is available on Moodle, and some more sample data I'll put in the video caption, a link to my GitHub site with some more bits of image processing code in case you'd like to have a look at some methods for doing some basic things, such as asking the user to put some settings into a dialog box in Matlab. Some basic examples like that. Right. So far in this course, we've mainly looked at Bayesian data analysis. We've looked at some of the principles of learning from data and the mathematical methods using Bayes' rule, and we're talking in terms of probability as a degree of belief in some statement. In this next part, well, two parts, we're going to look at image data, but then once we've got some quantitative results from image data, we're going to actually look at how we can apply the Bayesian ideas to results from image data using something called a Bayes classifier. So in that way, and this will be a way of in some image data deciding what sort of objects we have present. It's one of many possible different ways for doing that. Many more methods exist building on the basics, which we'll look at in these two videos, well, in these two parts anyway, on how to get results, numerical results from image data. Once you've got those numerical results, there's a lot of different ways that you could classify them, and a good deal of lecture courses on different methods, like, depending on how you're doing it, support vector machines, k-means clustering, all sorts of fancy, often machine learning methods. We're going to be looking, given the time available in this course, at basic methods to get numerical results from image data in Matlab, and then a Bayes classifier for interpreting those results. Okay. Right. We said in the last video that there are four aspects of doing image analysis, those being some details about how your image acquisition works, for example using an optical camera. Second, some questions about how the optical image is stored as discrete data, usually as a rectangular array of pixel values. Third, some detail about how you extract quantitative results by doing some analysis of the captured and discretized image data. And then once you've got your results, a fourth step, your interpretation or your visualization of those numerical results. So we went through last time the idea that, well, let's assume for now we're considering optical image formation, where your scene in the real world is turned into a light intensity distribution on an image sensor, which is then sampled. So you end up with discrete samples in space, in X and Y, on your image sensor, corresponding in some way to the real world, and some details to do with what bit depth the light intensity levels are discretized. For example, you might just get a load of numbers from 0 to 255, where 0 is no light and 255 is your maximum light intensity. That's what you get as your digital image data, and the question is, given you have that acquisition procedure, how do we then deal with the image data? Bit of a recap. So your digital image is sometimes written as I, algebraically, and for a number of positions, so position P is a row and a column within your rectangular image array. You have a load of intensity values, I at position P. you might come across the phrase pixel, so that just means a position P, usually in 2 dimensions, but could be in 3 dimensions, and the intensity value I at position P. Okay, so that pair, position and intensity value, is called a pixel, and you have your discrete data, which is discretized like that. We looked at doing that for something like a grayscale or monochrome intensity image, and we had the idea that we have a load of pixel values. So you're a rectangular array. For each position you have some value between 0 to 255, and in some image formats the numbers might not be 0 to 255, they might be floating point numbers scaled between 0 and 1. And sometimes in Matlab, if you that might cause you problems if you interpret your data, which is actually 0 to 1, as if it should be 0 to 255. Often functions will deal with this difference intelligently, but they may not, and you should be aware that it exists. We talked about red, green, blue image data, where you have the same list of pixel values for 3 different color channels. And what did we say we could do with that? So in general, suppose we've got some image data. Let's say in general, what are we going to do to process it? Well, the basics are usually written as we're going to do, we're first of all going to read in some data. There's a Matlab script on the Moodle and will be available on Github for looking at some specifics. So, well, there's some sample data, a sample image, which I'll show you in the next few slides, and some Matlab commands to read this in using imread and the file name, and then to do some basic processing of this. And the basic processing is typically done, at least to start with, we do what we could call segmentation, analysis, and visualization. Or sometimes these are written in image processing textbooks to be more memorable. They're sometimes called recognition, registration, and reconstruction. What do those things mean? So given a digital image, segmentation usually means finding some feature of interest within the image data. Analysis could mean an awful lot. It might mean dealing with lots of different images and somehow finding the same feature of interest within each of them and pulling out some values for it. In the basic example I'm going to show you coming up, we're going to do segmentation to find some features of interest, which is a bunch of grapes in an image, and we'll do analysis, just pulling out a simple property, namely the size, the area within the image data of a bunch of grapes, and then displaying the results. Visualization could mean a lot of different things again. You could just draw a table with your results, areas of different objects that you found, or you could do some fancy visualization. Those, anyway, segmentation and analysis or fitting and visualization, these are the basic steps in most image processing pipelines. You might find them called recognition, registration, and reconstruction. Right. So here's some sample image data. You can download this from the Moodle, and I will put up some scripts as well on the Moodle. Here's the start of the script for reading this image data into Matlab and doing some basic processing. So what are we particularly? Well, we're interested in cropping, either taking your red, green, blue image data, and I'm particularly interested in pulling out the numbers for the red, green, and blue channel individually. Then we'll talk about a basic procedure, thresholding, so seeing which areas have at least a certain intensity value, at least a certain pixel value, maybe just in one color channel. And then we'll look at the improps function for looking, a regionprops function for looking at the quite a lot of different properties of simply connected areas, in other words, single lumps which have been detected by thresholding. So let's look at the some features involved in that. So here's your a beautiful picture from a garden of a grapevine. It's got some leaves which are green and red. It's got some grapes which are a nice darkish blue colour. So when I say they're darkish blue, well, they've got some blue brightness, but if you look in the red and green channel, they should be pretty dark. They don't reflect much green or red light. They do reflect some blue. Okay, so how can we see this? Well, you can read, first of all, let's say imdat, image data, you say is imread, reading the image from the file grapes.png. And then I've said, in a few different figures, show me imdat, image data red is image data : all rows, all columns, but layer 1, which is conventionally, as in this image, the red channel. Likewise for layers 2 and 3, the green and blue channel. And I've showed that as a number of subplots, and for each subplot I've said image SC, show the image scale color, for example for the red layer on the left, and I've said give me a color bar and also make the color map grey, which means I want to show the brightness of the red channel in a visualization where 0 corresponds to a black pixel on my screen and the maximum brightness corresponds to a white pixel in my visualization, and you've got a smooth grey progression between them. If you don't give it color map grey, you might end up with color map jet or some other default color map, and it might be difficult to interpret. So if you've got single color channels, it's visually easy to interpret. Well, this is the total brightness coming through, say, the red filters, or the total brightness in terms of the amount of red light arriving at my camera. That would be a perfectly good way of visualizing this data. You might want to color map it in some other way. We can look at how to do that. I believe it's in the sampled. I believe it's in the sample scripts. But you would simply either apply a different color map, or you, for example, you could produce a color map where you have, for your red, green, and blue channels, your visualization goes from black up to full brightness red on the screen, but with no green or blue. You can obtain color maps for doing that. It's not really very important. This is just in terms of visualization. You might sometimes find this actually producing a red, green, and blue image separately to visualize the current color channels. You might prefer that. I personally would probably stick with just showing a grayscale image for each color channel. Okay, so we've done that. That's just reading in an image and showing that we can pull out an individual color channel. What can we do with that? Well, the simplest, probably one of the early things that you can do, is you can apply thresholding. So thresholding works as follows. Again, there's the script for doing this is available on Moodle and probably also on GitHub. I want to take the numerical values within the image data for a couple of channels. The blue channel and the red channel I think are interesting, and I want them to use those to roughly identify where are there some of these blue grapes in the image data. And my actual image data itself is numbers for each color channel, which are in the intensity range 0 meaning dark up to 255. I'm going to produce a new image, but this a new image object in Matlab. But I'm going to do this. It's going to be a logical image. So I'm just going to say mask blue-ish. That's my name for a logical mask. It's going to be a rectangular array. It's going to look like an image, but it's going to be a rectangular array of zeros for false and ones for true. It behaves in many ways like an image, except it only has two values for, well, false and true, or 0 and 1, instead of a range of values from 0 to 255. But still, a logical image behaves in many ways like an intensity image. there's no problem visualizing it using the same tools, for example. So I create a logical mask in which what I've done is I've told Matlab to apply a test and give me a true or a 1 in each pixel position where the blue brightness in the image data is higher than the red brightness. As it happens, that's a good method for finding the grapes, because the grapes seem to reflect, when we looked at the numerical data, they do reflect quite a bit of blue light, but not much red. So if we do that, we get mask blue-ish, and then we can just use again the image SC visualization tool to give me a picture of what this logical mask I've produced looks like. And I've given it a title. This pixels in which the blue channel is brighter than the red channel. And you see in my default color scheme, dark blue corresponds to 0 or false, and bright yellow corresponds to 1, logical 1 or true. And by and large, then at this point you say, well, visually, yes, this has done a decent job of working out what areas contain grapes in the image data. And the first thing that I do, having done this processing, I want to get a numerical result. So, okay, the simplest numerical result from this is how many pixels in the image contain grape. So I'll just say Matlab within this logical mask blue-ish, then brackets colon, just to consider each position just as a list, just sum the number of positions where this criterion was true. In other words, that there is grape. And I come up with some answer. I would need to know what physical area the pixels correspond to make this useful, probably, but I can say area of this bluish mask is 138,090 pixels, and that's how much grape there is in the image data in total. And that might be useful in some applications if you're doing some sort of quality control and you have a good mask which accurately detects a good quality product or bad quality product being scanned as it comes off a production line. That's possible. Actually, you probably want to do more processing than this with most image data, though. So let's look at this. So the problem with this mask is that actually you get lots of scrappy regions. So there's 2 or 3, well, at least 3 areas in the actual image data you consider bunches of grapes. There's the big one on the right, one on the left, and then one on the far left. And your mask detects those basically pretty well, and it detects some scrappy small areas too. So you might want to do some sort of processing to tidy this up. And there's a lot of different ways we could do this. We could talk about morphological transforms, which are methods that are applied to logical, mostly applied to logical images, where you've produced some sort of mask. And we could do that. Actually, let's talk first about a useful function in Matlab which you might well want to use in a basic image processing method once you've invented a mask that detects objects of interest. Let's talk about this regionprops function. So regionprops, which you can look up in Matlab. You could use doc regionprops. Or just Google Matlab regionprops and it'll take you to the help file for it. Does quite a lot of different things, but the idea is that you've ended up with some logical image, like your yellow, which basically shows you where there are bunches of grapes, and it also shows you a few other scrappy little bits of image. So regionprops, I apply this to my logical mask, and if I do that, it returns a property for each what's called simply connected object within the mask. A simply connected object is a contiguous area of yellow or logically true values. And for each one I can tell regionprops what to return, but I might ask it to return what is the position, in other words the row, column or XY center of mass of the object. the area. We already looked at a method for adding up the number of yellow pixels in the entire image data, just using sum and treating the mask as a list. But regionprops does this much more intelligently for each simply connected or basically contiguous area of grape. That's useful because once you get a list of positions and areas, you can say, well, for this particular problem, I've got 3 or 4 large bunches of large areas of grape in the image data. I can, if I've got the properties for each of them, the position, the area, I can ignore scrappy little bits, which are just a few yellow pixels together. I can simply exclude all of the things which are smaller than some size of interest, and then I can get down to the areas which are genuinely, let's say, 4 different areas of grape in the image data, and I can get the area of each one, and that might be useful for something. Okay, so let's just look at applying that. I would normally sort of demonstrate this in Matlab, and it would be helpful for people to ask questions, very probably. But I will talk through just some of these functions that I think you will find useful for doing a basic task. I'll talk through these. So we've opened up the image data. We've created this mask blue-ish, and I want to learn about the areas of interest within the image data. So I say, I'm going to use this regionprops tool, which, once I've identified areas of interest, it does the annoying tasks of finding simply connected areas and the properties of those areas. So I'm going to say stats, which is an output this function will produce. It comes from the regionprops function, and I tell it, well, I want a table, please. I want a table by looking at mask blue-ish, the logical mask, and I'll have values for centroid, which gives me positions, area, that's the total area in pixels of each of these simply connected areas. Excuse me. I would like a bounding box, that might be useful. A bounding box just gives you the coordinates and of a rectangle which fits around each of the simply connected areas. The convex image is within that rectangle where the object is. That might be useful. The image is within the bounding box where the object is, and the convex image fills in holes and indents. So it gives you imagine a rounded image with any holes in the middle ignored and filled in, and indents in the edge filled in. But image you might find useful, for example. But the key things which it's nice to have are centroid, the center of mass of the object that you're looking at, and the area in pixels. And then because you don't necessarily like Matlab variables in tables, you say mask centers, the center positions is stats.centroid. This will give you proper vectors. Mask areas is stats.area, and so on. And then I'd like to just plot that, just so I can manipulate the data. So it says figure 7, make a new figure. Image SC. Ooh, that seems to be image SC show imdat layer 3. Well, let's actually show the blue brightness. So that's more like this image here. Show the blue brightness data, and you see I've got a load of red crosses have been put on this image data for some reason. Why is that? Well, those are your unfiltered, I believe, positions of yellow areas. So what are we doing with that? So we're showing the blue brightness channel in this figure, and color map grey for the blue brightness channel, and I'm saying scatter after hold on, hold off to plot on top of the image data a cross for each center position of a simply connected yellow area, and I've said mask centers all rows column 1, that's X position, and mask centers, all rows column 2, that's a Y position, and for each one just RX, put a red cross using your scatter function. And if you do that, you should get a result like this. And you say, well, that's horrible, because actually there are 4 bunches of grapes which are of interest, but I've got most of the crosses which I'm showing on this are scrappy background from individual pixels which happen to be either surprisingly bright blue or low red brightness, because my filtering method wasn't very good. You could get rid of these in a complex way using morphological transforms like imclose or imopen. You can look at what those do, and they may be useful, but in this case you don't need them. We can do a simpler quality control method, which is the results of which are shown on this picture, just by selecting only simply connected regions which have a big enough area to be of interest. So let's briefly look at the code for that. So this is pretty easy. I want, given each of the simply connected areas which were detected, for which I have a row of my arrays, mask centers, mask areas, etc. I want to get rid of the ones that are too small to be interesting. So I say, the way I've done this here is I've said list bad, so list of simply connected areas from the complete list which are too small to be interesting is just when the areas, mask areas, is smaller than, I've chosen a suitable value for this image data, 20,000 pixels. And for each of those, I see I've put in then a Matlab line for throw away from each of my results vectors that row. There are other more efficient ways you could do this by throwing away a row from a table of data, but I've done this by saying things like mask centers for each row when a list bad equals or is true, is 1, delete that row. And I've just applied that to each vector. Other ways of achieving the same effect, but this is good enough, because then what I do is I say figure 8, image_sc, use my image_sc function to show me the mask blue-ish, mask where I have grapes in my image data. I've applied axis equal, that's just handy sometimes for image data. It means that the image data is forced to be plotted using a square grid in the visualization. Useful so that your image doesn't get squeezed horizontally or vertically, which can look horrible if it's applied to image data. So I've showed the mask, the logical mask, and then I've said scatter mask centers X position and Y position, and plot a red cross. And you've got 2 red crosses because all of the other areas have been deleted. So that's useful. Within some image data, I found objects of it. I found regions of interest, and I've quality controlled down to just 2 regions for which I think these are objects of genuine interest, and that's a small enough number of outputs that I can do something useful with the result from them. So that's a basic method of getting a numerical result from some image data, and then once you've got your numerical result, you would do some interpretation. The interpretation here would probably be given some sort of scale, work out how much grape you could expect to harvest from the scene shown in this beautiful photograph. We've talked there about identifying objects. We've actually talked about grape detection. We could talk about other kinds of detection. And what we'll go on to do is talk about classifying objects. So using properties like area or the brightness of the object that might be useful. Since we've using regionprops, we can get the exact area where some object is, so we can get properties like how bright is it in each of its color channels. How do we use that for classifying? we might just want to classify using the area, which was already available through regionprops, or we might want to obtain some more data before we do classification. So let's go and undo some more about that, well, shortly. But actually, let's say something about describing image processing, because what you will want to do in this course, you'll want to be able to do a basic image processing thing that gets you numerical results from your image data, like areas of objects, and then you interpret that further. But let's say something about how should you go about describing an image processing thing that you're doing. So there's two things that you should do, and one thing that I think you should avoid doing. The two things that you should do, first of all, describe the task. Describe the way the image data was obtained. In the case of the bunch of grapes, I took a photograph in a garden with a particular camera. In a lab, you'd want more information about the optical setup, and you might give a full figure of your imaging thing, of your imaging setup, but do describe how the data was obtained, if that's something that you have available. Second, algorithm. Do describe the steps which were applied to the information, and in image processing it's especially nice to do this as a flowchart. This is just from one of my papers. I'll put the link in the video caption. It says that we start with a series of images of some sort of object, and for each image in the series we apply a segmentation step, which is finding bright spots. That's very similar to the thresholding step that I just said we did. For each bright spot we learn some useful property. It's actually, in this particular paper, we learn a center of mass position, so essentially we do regionprops centroid. Actually, that's not exactly what is done in this paper. I do something slightly more sophisticated, but we get the center of mass roughly of each bright spot, and that's a numerical result. We also get some other data for each bright spot, with which we do some quality control or some judging. In this particular paper, it turns out we're keeping data from spots which are sufficiently bright and throwing away data from spots that are not bright enough, in the same way that in a couple of slides earlier we threw away results where the area entry was too small. In this paper I'm throwing away spots that were too dim, and I'm throwing away a few other spots which had too large an ellipticity. And then with the good quality estimates of the center of mass position, then I'm doing some sort of reconstruction. Essentially I'm doing a density histogram of the points that I had detected. You can read more about that in the through a link in the video caption. However, key thing to say here, I've got a flowchart which just shows the 5 steps of what I've done in the image processing, and I've got a figure caption which describes what I've done. And this is a good way of describing image processing. What I would avoid doing is writing in a report a detailed description of which Matlab library functions were applied. This usually is not what you need to describe when you're presenting what image processing was done. Usually you should have a flowchart, and it might show you the some nice images or the results of processing at each step, or it might show you just a flowchart with names of processes that were applied. But I would avoid writing long bits of essay or paragraphs about particular functions that were applied and threshold values that were used. That's usually not important information. If you have to do it, you normally want to provide that as a supplementary information for your paper, because people won't want to read that in general when they're going through a report or a paper. Or sometimes if your paper is about something very technical, you might need to provide that information in an appendix or in the materials and methods section. But in general, for general saying what you did in some science project where what you care about is the result, the observations of the real world. You probably want to give a flowchart to describe what was applied, but not spend lots of text describing the exact functions that were applied. In other words, you should come up with reports which are short, and they have flowcharts or pictures which visually describe your image processing step. That's one of the nice features about doing image processing, is that you can have naturally the subject matter allows you to have good pictures of what you're doing at each stage of your processing. So that's a useful hint which you might like to follow when describing image processing. Use flowcharts with pictures, maybe, not long, boring prose, which is very hard to write and just as hard to read often. Yes, I've just got that final comment there. Implementation, software level, hard to describe in words. The result is often pretty boring to read. Much better to give people a flowchart. That said, do provide open source code when you're publishing papers, and some sample data so that your, for example, if you're publishing a paper, do give a link to your GitHub site or some other repository where people can download some or preferably all of the data you used, and the, say, Matlab code, which you click run, and it should act on the sample data and produce the graphs in your report. That's really helpful for people to have. But, well, if you provide the sample data or all the data and a Matlab script, you can, in practice, when you're publishing things, you can get away with just a very brief flowchart in the actual paper or article, and that's helpful. Good. Let's go on to look at a particular example of image processing relevant to the task for this course. So we have this particular task. There is some image data, and you see there's these assumptions which we are given, which are true for this image data. This is the way that some photographs have been taken, is that we've got some UK currency. These are coins on a green background. The coins themselves are not green, so that's helpful. The coins in the data set that we're wanting to be able to analyze using some software, the coins are separated so they don't touch. If they did touch, then like the overlapping grapes in the earlier image data, that would make them harder to deal with. We can also say the lighting is approximately uniform across the image. It's not perfectly uniform, but there's no problem of half the picture being in dark shadow. The scale or magnification is constant for all the photographs. That's an important piece of information to know. And we also can say that in all of the images we're looking at, there's a border region of the image which can be cropped out and ignored. We're only interested in coins within the middle of the photograph, and there's a training data set, so we see the region of the photograph in which there might be coins. And then the question is, can we count the value of the coins using some image processing method to extract information about each one, and then some sort of classifier. And let's look at an example of this being done to prove that it can be done. Let's then leave you to read through the assignment and do some Matlab and some writing up of that. But let's see that it can be done first of all, and then let's go on to look at Bayes classifiers, which are an example of a method which you could combine with the thresholding method in order to do that. So here's some example image data and some coins on a green background. This is from a data set available on Moodle, and the question is, can we take something like this data set, this image on the right, consider that as raw image data, and do some sort of object detection using a thresholding method similar to what we've looked at for looking at bunches of grapes. Maybe then use the regionprops tool to work out some useful things about the coins. There's a lot of properties you can look up from the documentation apart from just area. Also, you can get, well, you can get the some measure of how circular the coins are, which may or may not be useful. But you can also get something like the convex image, or the image within the bounding box. From that you can pick out maybe something from the color channels of each coin. The point is, it should be possible to learn enough about the coins. Maybe the area will do it on its own, perhaps, although it's not necessarily perfect on its own. Can you take that information about each coin and classify using some method? Here's my particular method. Can you classify for each coin what its value is, and can you produce a visualization of that, and can you also come up with a tool which returns to the Matlab console maybe the total value in a particular image? Well, clearly from the fact I've got some bit of software that has done this, this is quite possible to do using the basic methods of thresholding and some method of Bayes classifiers, which we will come to in the very next part of this video. So, data analysis part 11, Bayes classifiers, or Bayesian classification for results from image data. What shall we say about that? So classification is an important task using photographs or video image data. What is classification? So which class of objects does each sample correspond to? Available information for answering this task, usually some training data, either piles of experimental results, or sometimes some description of the classes of objects. So for coins, for example, you could easily look up a specification on what are their dimensions. Or alternatively, you wouldn't necessarily need to do that. You could just take previous sample image data, and if your new image data that you're going to want to process is obtained in a consistent way, then you can not bother about turning physical specification into a classification in some pictures that you've taken. You can just look at the properties of previous pictures that are taken and classify a new sample, a new coin, by assuming it's consistent with previous previous image data. There are lots of different ways of doing classification. Lots and lots. We'll talk about a couple of simple methods. Others build on the same sort of inputs that we would use for these, but they come under a lot of different names. Method 1, direct segmentation. So we have here a picture in the top right, a field of coins on a background, and using the methods we've looked at already of thresholding and regionprops, we've pulled out some properties for each coin, for each object. I've possibly tidied up to remove any stray individual pixels so they don't feature in the objects we've detected. So we've done segmentation to detect individual coins. We may have done some quality control to get rid of any problems of objects completely the wrong size being detected as coins. And then I've got a scatter plot. And in the simplest case, you can ignore the y-axis of the scatter plot and just look at the x-axis. I've got area of different objects which have been detected, different possible coins. And you say that because I know different coins have different areas, I can actually do direct segmentation using vertical lines, mostly within this scatter plot. And I can say that any observations between particular, within a particular minimum and maximum must correspond to a particular coin. So, for example, the smallest coins, the ones to the left of my 30,000 pixel line, the smallest 3 coins must be 5p coins within this image data. You can find out suitable sizes in pixels from training data. That's direct segmentation. You might need to do more. You might find that some coins are sufficiently close in size that the classification is ambiguous, and you might apply additional greater than or less than steps to sort a new sample into what type of coin it is. And for example, I've got a y-axis. That might be some other property of the coin if you need a property other than just size. And you might well need that. And we've talked about using region props to get the position of each coin and the image, or the within a logical mask, the pixels which correspond to it. You could pull out from that, let's say, the brightness of the red channel of the coin, or of the blue channel of the coin. Something like that you could experiment with, and that gets you a y value. And then you'll see that the sometimes, such as for the second smallest set of coins, when size alone wasn't sufficient to distinguish, that might have been 1p and 20p coins, some other parameter, which is easily pulled out of using region props from the image data, allows you to do direct segmentation. This is great if it works, but it's a very crude method, and we'd like to pull together processing of image data to do classification with the Bayes rule methods that we've looked at earlier in the course. To do that, we'll use a simple version of how to do this, something called a naive Bayes classifier. The word naive, don't worry about it. It means that we're interested in simple cases. You can look up what that means mathematically in textbooks or literature, or Google the distinction between naive and, well, you might say full Bayes classification. For now, it just means that we're going to be getting a couple of different measurements in order to classify something, and we're going to assume they're both useful and independent. That's roughly what it means. And we're going to use a couple of different measurements of some coin to work out what class does it fall into. Before I consider, or instead of considering doing that for coins, let me imagine you've got some aerial imagery, and in your aerial imagery of the countryside, you've got a few different types of things. You might be looking at a rural area, and the three things of interest which you can detect using a segmentation tool might be solar photovoltaic sites, wheat fields, and apple orchards. These things might have different sizes. For example, let's say wheat fields are large, apple orchards and solar photovoltaics are generally small. In that case, if I classify just on area, it turns out that a vertical line in my scatter plot isn't enough to completely sort out what object I'm looking at. I can add a green brightness channel as well, in which both of the crops are green. So in that way, I can say large on its own, or large and green, corresponds to a wheat field. Small and green corresponds to an apple orchard. Small and not very bright green corresponds to a solar photovoltaic site. That's direct segmentation, but might not be very good. Oops. Okay. What if you have more awkward cases than that? So, for example, in this new training data set, I have rigged it so that the data I need to sort out has an unhelpful overlap, so that I can't use a straight vertical line and a straight horizontal line on their own to distinguish these sites. There is instead a nasty curved line, and this is just in the training data set, distinguishing the cases. Well, what could I do there? Well, I could take lots more cuts, but this clearly becomes very fiddly and cumbersome and not suitable for real data. What I want to do, and there's a lot of ways you could do it, we'll look at Bayes classifiers, is some way of intelligently looking at the data and hoping that you have... I've moved the points because this makes it easier to draw the ellipses to describe what we're doing. We're wanting to say these objects that I'm trying to classify fall into particular regions of in this case, my area and green brightness scatter plot. But here are some not regions that are rectangular. These are in general ellipsoidal regions of confidence. and I want some way of classifying the objects I've got into 3 clusters, not multiple segments. I might be interested actually in this case. So the case that was difficult for using straight horizontal and vertical lines to do direct segmentation, classification that way, I can do quite a bit better if I consider using Bayes' rule, some sort of ellipsoidal region for each type of land application for each object I'm looking at, and there might be some way that I can use that information to get not a yes-no probability using hard rules on sizes and green brightness, but I might be able to get a probability that an object falls into each class. And if I can do that, that would be useful because it would tie together pulling data results crudely out of image data with doing good Bayesian learning from the results. So how might I do that? Well, I might use naive Bayes classification. So we will recall from the handout, Bayes' rule, the probability of an individual hypothesis given the data. In this case, the data is results, area and green brightness from the image data. The probability of hypothesis I given the data is just given by the expression. It's the probability of getting the data if the hypothesis is true, times by the prior probability of the hypothesis, normalized by the total probability of getting the data. My hypotheses could be H1, H2, and H3 for the object being a solar photovoltaic site, an apple orchard, or a wheat field, and I would have no problem saying I'm indifferent. I have a flat prior. The prior probability for me, knowing not much about land applications, it's a third for anything I'm looking at being each of those things. Then you say let some data, dj, be the observed area and green value for the jth object, so area j and green brightness j. Don't worry too much about what naive means in naive Bayes classification, but I want to invent a suitable probability distribution for getting the data on each hypothesis, and if I can do that, then I can invert that and learn the probability that each hypothesis is true, and then hopefully I can say the most likely hypothesis is my classification, and also I'll get as a bonus a sense of how certain we are that the classification is true, which you don't get in the direct segmentation method. So, invent. By inspection, let's just invent a two-dimensional Gaussian and assume that's adequate for saying the probability of getting the data dj on each hypothesis hi. It's given by this equation, a 2D Gaussian. And how do we do that? Well, we might invent Bayes classifiers, and that is something that you can have a look at in the sample Matlab scripts that are on Moodle. But you might have something like this. I'm considering a range of possible areas of an object, a range of possible green brightness values that I've detected by image processing. I've got this mesh grid, in other words, just a list of all the possible areas combined with all the possible green brightnesses, like we did before for the example of apple tree heights in chapter 5-ish or something in the handout. And I could look at my training data set and I could find what is the what are the parameters that describe a Gaussian for the probability of a particular area and green brightness for each type of object. So I've got types 1, 2, and 3 for different types of field, and a typical area for each of the 3 classes, with the wheat field, case 3, are being much bigger than the other 2. Likewise, the green brightness for the solar thing being much lower than the green brightnesses for the crop fields. I also define some variances for each Gaussian. And then I just get the probability of seeing a particular bit of data given each hypothesis. And then if I say I've seen a particular object area and green brightness, that's all I need to do to invert that is use Bayes' rule, or in fact, all I need to do, I can produce actually a visual inversion for this nice simple case. So naive Bayes classification, these are plots of the probability of getting some data, a particular observed area and a particular observed green value on each hypothesis. You see these form 2D Gaussians or ellipsoidal regions, and that is realistic. That corresponds to the sort of spread that I saw in reality. And that means that given those probabilities, what is my probabilities of getting the data? I can invert that using Bayes' rule. Have a look in the script if you want to follow through exactly how to do that instead of by following through in algebra. But I can invert that, and I end up with something like this. So I get a probability, for this problem, three different hypotheses. I work out the probability of each hypothesis given each position in the two-dimensional mesh grid, each possible observed area and green value. And that works very nicely. So for an apple orchard, I see things that are small and quite brightly green have a high probability of being that. For solar, things that are variable in area but generally small in area and not bright green are solar farms. And then I've got a bit of a mess for this wheat field. So the wheat field, it should really be large and green, but actually I need to slightly improve my method because this hypothesis has picked up all the dross as well, and that's because I had a large variance for my wheat field parameters. So I just need to slightly improve on this. I'm happy with this classification, well, the other two classifications, but not for wheat. And how can I fix that? Well, I've got, it's because so the reason this comes about is because I've only got three hypotheses. And even though for a particular thing, like a very small area of 0.1 and a very bright green value of 1, there's a very low probability of getting that from any of the hypotheses, but because the wheat field has a bigger variance, it has the biggest of the small probabilities. And this classification method says a field which is actually nothing like wheat gets classified as wheat. I can fix this. How can I fix this? Well, in a naive Bayes classifier, instead of just having three hypotheses, one for each class, I want to add a fourth hypothesis, which is that I've made some sort of mistake or something which has occurred which is outside of my three classes, or I call this an out-of-universe error. Where I've got this is I've just, for my probability of getting the data in total, I've said that this might come about not just from each of the three hypotheses, which you've got in the denominators here of these terms. I've also said there's a flat, and I've manually chosen 0.0001 probability of getting a weird result from some other hypothesis, and that amounts to hypothesis 4, that the data is coming from something other than the three classes I'm interested in. If I do that, that tidies up the stray areas on my wheat classifier, and so we're down now to only things which are large and of realistic green brightness get classified as wheat, and the other two things, the apple orchards and the solar farms, still get correctly classified. Okay, so that's naive Bayes classifiers. That's taking the results from image processing and applying Bayes' rule to do object classification. So that should be a useful method. If you go to the GitHub, which is quantitative imaging / pyrometry, you can get some scripts for doing general image processing, reading in and getting prompts about how to process image data, if that's something that you want to be able to do usefully in Matlab. So for example, this is for a different project, but if you wanted to be able to specify a load of parameters within your image data, then you might want to use some sort of a graphical prompt command rather than, it's generally better to do this rather than make people type at the command line instructions, because people can usually follow a graphical interface better. It also avoids the problem of having to manually edit a script in order to run it on some particular data. Instead, you can just run it, and any variables you need to set can be set in a dialog prompt. That can be useful. There's just some examples on the GitHub if you need it of how to set up a prompt and get values from a prompt. Although you don't need to look on the GitHub, I've also put it in the slides here, which you're welcome to read through. I will also put in the video caption a link to some of the an example of how to write up image processing. Just one of my papers without having to without describing too laboriously in prose, but instead using flowcharts. And with that will hopefully be plenty of data for you to get on and write a Bayes classifier that does something useful. Right, good.